Now let's continue on page 225. We'll do. We're still in section 9, chapter 9.4, and we're gonna do geometric series. The geometric series is something that looks like this. Here's a famous geometric series, which is actually I don't know how famous it is, but it's a common one. And it say if we have something called 1/2 plus 1/4 plus 1/8 plus 1/16, what is special about this? The difference of is not constant. However, the ratio as it goes down is constant. That is, each time this thing is being multiplied by 1/2. You see, 1/2 times 1/2 is quarter. Quarter times 1/2 becomes 1/8, and 1/8 times 1/2 becomes 1/16. If the ratio between these numbers are constant, the ratio is called R, okay? In this case, R equals 1/2. If the ratio is constant, it is called the geometric series. And the geometric series has a very convenient formula to calculate the sum. For example, let's look at the page, the same page in the middle of the page where we have this part right here. Okay, let's look at this. Well, this will help us find the this part here will help us find a formula for the geometric series Sn. Sn means the sum adding all the way up to the nth term. This is the first one and second term. And let's say you add up. Right now I have 1, 2, 3, 4. So if we don't worry about what's left, I mean the rest of it, then this will be called S4. It's just that means the sum of the first four terms. Now, generally speaking, we can come up with a formula for this sum, and the formula is derived like this, as the book shows. Now, and let's see what this means. Now, we write down Sn, then in general will be A1. In this example, A1 stands for 1/2, and then plus R times A1. And where R is 1/2, okay? So our A1 is equal to 1/4 plus R squared A1. And then so R squared is 1/4 times A1 is still 1/2, so that becomes 1/8. So that's that one. Plus and etc. all the way down to R to the power n minus 1 A1. So that is called Sn. So this is so there's a total of n terms because this is the 0th term. Okay, this is this is a to the power 0 effectively, and whereas this is the a to the power 1. So if you go like this, if you go all the way to Rn minus 1, then you have a total of 4 terms. I'm sorry, total of n terms when you count that way. Because from A1 to n minus 1, there's n minus 1 terms, and then there's one more at A0 that gives you a total of n terms. Anyway, so this is the nth partial sum of all this stuff added together. Now we're going to derive the formula for Sn, then we're going to pull this trick. We're going to multiply R times Sn. And so what would that give us? That will give us R times A1, okay? And this is to the power 0, which is, well, let's see. I'm missing something here. Actually, I said that wrong. This is not a to the power 0, because a to the power 0, anything to the power 0 will be 1. I just mean, I don't care what I mean, okay? The point is, this is the first one is just A1, the first number, which in this case is 1/2. But anyway, we will, if we multiply everything by R in the whole series, then everything in here gets multiplied. Then we will have R A1, and then plus R A1, R squared A1, and then let's see, I didn't write this properly. And let's see. Okay, we're not going to do that. What we're going to do is multiply by minus R A1. Minus R on Sn. That is, this whole thing will multiply by negative R. If we do that, then we will get minus R A1, okay, and plus, and then minus R squared A1 because this is this term times minus r. This one is that thing times minus r, etc. Okay, and then all the way to this one becomes minus Rn A1. Yep. And then what we're going to do is add up these two equations, and if we add them up, what we have here is there is one more term here. Okay, I should write it out. This goes all the way to negative r minus 1 an, and then finally to minus r n a1. There, that's better. So these things, I'm just moving the whole column over one spot. Okay, so then let's add these two things together. If we add them together, we will have this part becomes Sn minus Sn minus minus Rsn, which is the same as Sn times 1 minus r. That's Sn minus this. Okay, I mean, yeah. Anyway, so basically we're adding them together. So see, so this is becomes Sn becomes 1, okay, and then minus r, and this part, all these things cancel out. See, I mean, all this stuff all the way here. The only thing that has left is a1 in the beginning, and then minus r n a1 at the end. I mean, that's it. So then we can write so this thing, imagine it clear over here. So anyway, this in other words, Sn is given as is equal to the numerator, which is, we'll write it again, which is a1 minus this thing Rn a1 divided by this thing right here, which is 1 minus r. Or put it, or we can write it another way, factoring the a1 out. We will have a1 1 minus r to the power n divided by 1 minus r, and that is the formula for Sn. In other words, if we want to calculate Sn to any number, like 100 terms, okay, I would need to know this thing adding up all the way 16, 1 over 32, 1 over 64, and goes on until we have 100 things all added up. What is the sum? Instead of doing 100 additions, we'll just plug it in right here with 100 right up there, and r equals 1/2, and out pops your answer. Okay, so that the formula is very handy that way. And then let's look at the next page and consider example 4. Okay, let's see. Let me write this down. So here I wrote down example 4 on page 926. We have, let's do part A, where we need to find S11. That is the first 11 things added together, and what might it be? So we'll follow this formula right here, where A1 is the first term, which is 8. So A1 equals 8. Let's remember that for a second. The second is, what is the R? R equals the second term divided by the first term. Or the third term divided by second term, doesn't matter, it's constant for a geometric series, and we know this is a geometric series because the problem says so. Therefore, the R is equal to -4 divided by 8, which is equal to -1/2. Or equals to 2 divided by -4, which is also -1/2, which checks out. If it isn't, then we'll have a problem. But anyway, so S11, by this formula, following this formula right here, S11 then equals to A1, which is 8, times 1 minus, don't forget the negative, okay, minus 1/2 to the power of 11, because n is 11 is what we're looking for, and then divided by, divided by 1 minus -1/2, which means we're going to be adding, okay, which is okay. So now that we have that, let's pull out the calculator and see what it says. Let's see, to do that, I need to find my calculator. So let's do this thing, okay. First, let me turn my calculator on. We'll do 8 times 1 minus negative, so 1/2, so let's put another parentheses in here, And 1 negative, what am I talking about? Minus 1 divided by 2, that's 1/2. Okay, to the power, raised to the power, right here, raised to the power 11. And then, okay, and then get out of the top, close parentheses. Okay, that should be the end of the parentheses on top, divided by 1 minus, let's do parentheses again, 1 minus negative 1/2, that's 1 plus and a half, that's 3/2, okay? So divide by 3/2, close parentheses, okay? That should give us something. What is that? I don't know, but let's, is that right? 3/2, let me check. That doesn't make sense. Actually, it does make sense because this thing is going down, into fractions and into a weird number, so it's not going to be a very nice number or anything. Yeah, it equals to 5.33, etc. And let's see. And the book says that's correct. Okay, so that's always good to find the same thing the book says. All right, so I'll put the calculator there. That's part A. And then let's look at part B. We're doing the sum of, okay, let me write it down. Okay, I have the problem part B written down as the sum of k equals to 1 to 6. The book have it in a weird way, but that's not how it's supposed to look. Okay, there's probably a mistake in there to put all the numbers in a weird location. The 6 is supposed to be on top of the summation sign, and k equal to 1 is supposed to be on the bottom, nicely lined up like this. But anyway, so 3 times 2 to the power k, so which means there are 6 terms. We can write it out to see what these things look like, but we don't have to. Okay, we just need to figure out what these numbers are. First, a1 would be equal to A1 is when k equal to 1, that's 3 times 2 is 6. So we know what A1 is. And then what are the ratio between two of these things? So let's say A1, we already know A1 is 6. Okay, what is A2? A2 would be 3 times 2 to the power 2, and 3 times 4 is 12. So that equals to R, which is 12 equal to 6 is 2. So the ratio is positive 2, so this number is doubling, okay, quite quickly as it goes from 1 to 6. Well, that means nothing to us. We just plug it into this same equation. The sum, we're looking for S6, right? So S6, following the formula right here, is equal to A1 6 times 1 minus R, which is R is 2, so 1 minus 2. And then on top is 1 minus 2, R is still 2, N is 6. So I'll write a 6 there. And then plug this out. Well, whatever. That's, yeah, let's do that on the calculator and not think any more about it. Now it's so 6 times all that stuff. Okay, so let's look at this. First, let's clear out the old stuff. And so we have, what was it? A1 is 6, all right, times, I forgot to type in times. I don't know if it matters. Sometimes it doesn't matter, but let's type it in for now. 1 minus 2 to the power, right here, 6, okay, and then get out of the power. And then close parentheses, that looks okay. And then divided by negative 1, because 1 minus 2 is negative 1. That should do it. That should give us a number, 378. All right. Let's see, where is the book? Here's the book. Let's check to see if I got it right. 378 is what I said, right? Yeah, it looks right to me. Yeah, it's a pretty straightforward formula. You just have to follow the formula exactly, and then the answer comes right out. And then what's this? Now next, so then let's look at example 5 after I clean off the board. So next, let's look at example 5, which is on page 927. We have some guy is starting a salary at 26,000, etc. And so we'll write that down as A1. Okay, A1 is equal to 26,750. All right, and then he has an increase of 1.6%, which means R equals to 1 plus, sorry, not plus, 1.16. Okay, any percentage always work this way. So that each year, then you multiply by 1.016, and that will be the increase, and that's the ratio of increase. And then for his total earning as 5 years, so n equals to 5. Knowing that, we'll just plug all the stuff right in this formula right here. We don't need to know anything else. Okay, so let's say, so the formula says the total, that's how much he made 5 years all added up, okay, every year summed. So A1 is the 26750 number times 1 minus R to the power, sorry, I should not write down R, but let's get rid of the R and put in, what was I writing? This number, 1.016 excuse me, to the power 5, okay, this thing to the power 5 divided by 1 minus 1.016. All right. And at this point, we'll hunt for the calculator. Here it is. And clear the old one, and let's actually, I think I'll stand maybe over here is better. Is that better? No, not really. Maybe this place is better. Let me see. Hard to say. Maybe over here. This seems okay. Yeah, we'll do this. Okay. Anyway, the point is, let's type this in. 26750 times 1 minus 1.016 raised to the power 5, close parentheses. Nope, wrong. Go back. Okay, you need to get out of there first. Yes, get out of the power signal and then close parentheses. Okay, that looks all right. And then divided by parentheses again. Okay, we need to do the 1 minus 1.016 close parentheses, because there's a subtraction there, so you have to do the parentheses. Otherwise, you will be only dividing by 1. Okay, that should be all right. 138,000. All right. Let's see. Does that look good? Let's look at the book. What does it say? 138,000. And then some $99. Yep, that is correct. So that's example 5. And so and let's continue to the next part, where we consider infinite series. Now, what happens with the infinite series is generally speaking, sometimes the infinite series will add up to be a finite sum. Now, how is that possible? Let's look at the example I gave earlier before, where I said that 1/2, okay, plus 1/4 plus 1/8, and etc. plus 1/16, and you get the idea. Okay, each time is half of before. If you keep adding this, following this pattern, that each thing is going to be half of before, then and do it in all the way unto infinity, the whole sum will add up to be a fixed number. Now, why would that be? This one happened to be equal to 1. Now, the whole sum, even though you have infinite amount of stuff that's being added together, it adds up to be a finite value. How is that possible? Or is this even realistic? It is, because that is how it works in real life. The example for this problem would be that, let's say you have a cake, okay, one cake. So the first thing you do is you cut the cake in half, okay, and then you eat it. So you have 1/2 left. So you ate 1/2 of a cake, okay? So this is counting what's in your belly. First you have 1/2. Then the remaining half, you cut half of it off and ate it. So now your belly has 1/2 and 1/4, and there's a quarter of cake left. Then the next step, you take the quarter and cut it in half. So there's an eighth of a cake slice. So you ate it. Now your belly has this much cake left. And you continue cutting whatever's left into exactly one half and eat the half and leave the rest. So you can theoretically cut the cake, continue to do this forever unto infinity, and the total amount of cake you will eat is still going to be less than one cake, okay? So that's how an infinite series can still add up to be a finite sum. Now, in fact, as time goes on, you have eaten most of the cake. Eventually, of course, you can say that the cake will be too small for me to cut, okay? And so this is not really practical, but that's the idea. So if you could cut the cake infinitely small, then you will have an infinite amount of stuff being added together that will still add to be a finite number, okay? That is, you will in reality is basically you will never finish eating the cake, and the amount of cake in your belly will get closer and closer to a whole cake, but it will never get there, and furthermore, it will never be more than one cake. You'll never be able doing this trick of cutting unless you sneak a cake from somewhere else. You're never gonna get to eat more than one cake, okay? Going through this process if you're stuck with doing just that. So anyway, so that is one idea of how an infinite series of numbers added together can actually add up to end up being a finite sum. So let's see. Now whether the series converge, which means it adds to a finite sum, or if it diverge, when it converge in your book's term, converge means it's defined. Okay, this thing will add up to be 1 or very close to 1. The farther you go, the more cake you eat as you cut, the closer to a whole cake that you're eating. So the answer is considered as 1. Now as a whole, if the ratio between these two things are less than 1, then the thing will converge. That is, the sum will be defined. Otherwise, if the ratio is 1 or more, then the sum is not defined. Okay, and the ratio can be negative as long as its absolute value is less than 1. That is, if the value is between -1 and 1. So let's look at example 6 to consider this. What is that? The ratio is, okay, right now we just have to figure out if the infinite series is defined. In other words, does it all add up to be a finite number, or does it go to infinity? The other option is when you have a bunch of numbers added up. For example, if we have, say, the numbers 1 plus 1 plus 1, and we'll just add it forever like this, that will go to infinity, okay? In other words, the sum is not defined because we can't define infinity. So that's the difference, is that the term, the ratio, see, in this case, the ratio is exactly 1. And at that point is the sum is not to be defined. So the only thing you have to think about is just the ratio. Okay, so let's look at problem A. Is this sum defined or not? Well, look at the first two numbers. We already know that it is a geometric series. So is it defined? Well, assume that we know that. Actually, do we know that? Yeah, let's hope we do. Okay. Now the ratio 8/12, that is, I'm looking at part A here, and we're 12 plus 8 plus 4. Okay. So looking at part A, we have 12 plus 8, etc. The number is going down. If this is a geometric series, then 8 divided by 12, the ratio is 2/3, right? Is it 2/3? Yeah, something like 2/3. The point is, it's less than 1. Therefore, this series, if it continues in that pattern, it converges. In other words, it is defined. However, in this story, however, the ratio doesn't even stay this. It's not. So first we have to figure out if this stupid thing is a geometric series. I thought they already given as geometric series. Fine. The first one is we have to first decide if it is even a geometric series. Now the first ratio is 8/12, okay, which is 2/3. But the second ratio, 4/8, is 1/2. So it's not even geometric. So why are we even talking about it? Ugh. Now let's look at part B. So part B is the first ratio. What is 1/2 over 3/4? That is 1/2 divided by 3/4. Let's write this out. We have 1/2 divided by 3/4. To divide is to invert and multiply. Okay, so let's, which means we're multiplying. Maybe we shouldn't write down that. Okay, 1/2 multiplied by what is the other? 4/3. Okay, I inverted 3/4. So 4/3. You cancel out that b equal to 2/3. So the ratio is 2/3. I hope. And then look at the second term. What is the ratio? The second term is 1/3 divided by 1/2, which is the same as times 2. So it's 2/3. So the ratio stays at 2/3. And in that case, being that 2/3 is less than 1, B is a geometric series. And so it is B is a defined, that is, it does converge. And then the third situation where we have the sum of k equals to 1, and this is a geometric series because we notice that this number right here, this number is what is the ratio. Okay, is being raised to the power k, and that's the ratio. And the ratio is 1/3. If the ratio is 1/3, then it is a geometric series, and it does converge, so it's defined. And finally, this one is this one D doesn't converge at all. I mean, D is just it's 5 plus 10 plus 15 plus 20 plus 25. I mean, that is gonna go to infinity very quickly. So that's example 6. Now next, let's look at the bottom of the page. We are now on page 928. At the bottom of the page, we have something that's interesting to think about. Now this is Sn, okay, which is 1 minus r to the power n and 1 minus r. Now what happens when n goes to, how do we calculate the sum of the infinite series? Then we have to let n go to infinity. Now anytime when you have a fraction and fraction multiply itself, it needs to multiply itself infinitely. So a fraction multiplying by a fraction is always smaller because it's a fraction of a fraction. So as it goes on, like in this example on this page, we have if r equals 1/2, 1/2 times 1/2 is a quarter. A quarter half is 1/8. In other words, a fraction, when multiplied by itself, is always cutting itself down, right? It forever cuts itself down, as long as a fraction in the sense that it's smaller than 1. So this number will eventually, as n goes to infinity, this number goes to 0, and therefore for the infinite sum, if it exists, will be equal to, so S infinity, that is the total sum, will be equal to, is equal to A1 divided by 1 minus r, because this becomes 0. So we only have 1 left, and the formula goes like this, which is a very nice and clean formula, by the way. Look how easy this will be to do. This is even easier than this one, because you don't have to worry about n even. You just take A1 and take r and plug into this thing, and then out pops your answer. Now to see how that works, let's look at the next example on the following page, page 929. Okay, now example 7. First, let's ignore part 8 because that's not even geometric. The thing is just going down by 1 at a time. Ignore that. So let's do part B. Okay, part B, according to the book, if you were to find the ratio between the two numbers, it is geometric. All right, let's double check the book to see if they are right. Okay, and just for no reason. We have, what are the numbers? I guess I'll write it down. So let's find the ratio of this thing. Well, anyway, let's see. Let me turn on the calculator. Okay. Anyway, let's see. What is the ratio of the second term of the first term? That is, what is 99.44 divided by 248.6? Is 2/5. That is, that equals to 0.4. All right, so this ratio equals to 0.4. I'll write that down. R equals to 0.4. And then what is the ratio of those two? Again, we have to do this. Next, we have 39.776 divided by 99.44. That is also 0.4. All right, so at least in this, for the first three things, this is R equal to 0.4 here. So then and then this goes on presumably. But at least this is, we assume that this is a geometric series because the first three numbers are in a geometric relationship. And then what is the total sum? And the ratio, more importantly, is less than 1. That's very important, okay? That is, the absolute value of the ratio has to be less than 1, or R has to be strictly between 1 and 0, 1. It cannot be 1 and -1. It cannot be 1 or -1. Okay, so R is 0.4, so let's plug it in here. The sum is equal to, and the infinity sum, we'll just write it as S, equal to A1, that thing, 248.6, and then divided by 1 minus R, that's 1 minus 0.4. Okay, so let's plug that in and see what it says. Let's see, clear that stuff, 248.6 divided by 1 minus 0.4, that's 0.6. Let's see, well, anyway, that equals to, what's that, 414.3. All right, let's see, is that correct? Part B, 414.3, that is correct. All right, so then that's part B. And then next, let's do part C, which is, okay, it has a specific ratio here, which is minus 1/3. Now, minus 1/3 is between -1 and +1, so that is a defined series. That is, this series will converge to a number when you add it from 1 to infinity. So let's write it out what it is. The total would be, for part C, A1 would be when k equals to 1. If you plug in k equals to 1 in this story, you get, then A1 is that number there. That is A1 equal to 4,374. And then what? And then following this formula, R is -1/3 equals to -1/3. All right, so that's it. Okay, so S equals to 4,374 divided by 1 minus -1/3. Okay, be sure to write the negative sign here, because 1 minus -1/3 is, if you're missing the negative sign, you're going to get a completely wrong answer. Because you're going to get a different answer, and any answer different from the right answer is automatically wrong. So we have 4,374 divided by 1 minus, well, that's the same as 1 plus 1/3. So I'll write it type it this way. That looks okay. So that equals to 3,280.5. Okay, let's see if that's correct. 3,280, is that what I said? 3,200, yep, that is what I said. So that's okay. And then the fourth one, you notice the ratio, right? The fourth, that is part D of the problem, says that the ratio, pay attention to the ratio here, see, it's 4/3. If it's 4/3, it's bigger than 1, and the series does not converge. That is, it is not defined. So we don't have to do anything. We'll just say it's not defined, okay? The sum, if it's not defined, the sum does not exist. So next, let's do example 8. Find the fraction for a repeating decimal. Okay. Let me write that down. So that we need to find the fraction for the repeated decimal 0.33333. Now we already know what that is. It's just 1/3. However, how would you find it if you didn't know that? So we're going to use this trick right here and write down 0. If the 3 is being repeated, is 0.3. The bar means repeat this thing forever. Okay, so that is the same as 0.3. Write it as a series, and plus 0.03. Okay, and then plus 0.003, and so on. Right? I mean, that would be something like that. And you notice the ratio between them is r equals to 1/10, right? Because this thing times 1/10 will be equal to that, and then that thing times 1/10 will be equal to that, and so on. And then let's apply this formula right here. So this infinite sum is equal to A1, which is 0.3, divided by 1 minus 1/10. And let's figure out what that is. That is equal to, and that should give us some kind of a fraction. Okay, so let's look at at least a fixed number, okay, fraction or not. The point is, okay, so let me do this. Now 0.3. Let's see, how good can you see this? Let's see, can I read it? Sort of. Okay, so 0.3 divided by 1 minus, what is that, 1/10? That's 0.1. Okay, I'll just type that in like that. It equals to 1/3. So my calculator immediately cranked it out. So this equals to 1/3. See, that shows that this formula actually works. See, because we are using the formula to calculate something that we already know the answer to. And if it doesn't work, then you know there's something wrong with the formula. But it does work, so that's good. And so that is example 8. Let's see, yeah. So next, example 9. Okay, example 9. We're going to look at something called an annuity problems. Okay, well that is, well, anyway, that works the same way. That uses the formula we had earlier, this one right here. Now the annuity problem goes like this. Let me clean off the board. So let's look at example 9 on page 931. We have some kind of a deposit of $100 is made every month for 10 years. Now the fund earns 9% annual interest, compounded monthly and paid at the end of each month. How much is the account after the last deposit? What that means is we have $100. Well, actually, it doesn't matter. Okay, let's just follow the formula because, yeah, this kind of stuff is not really worth thinking too hard about. The point is we have the A1 in this annuity problem equals to 100. And then the total, the N is counted in terms of months because the money is paid every month. And 10 years is 12 times 10 months. So the total is, this will be equal to N in the formula because N counts the number of months. And then the R is the interest rate per month. So that takes R is equal to the annual interest rate, which is a total of 1.09. No, sorry. R is equal to the interest rate, which is 9%, divided by 12. So we'll take 9 divided by 12, and then that is that's the interest percent. Okay, and that equals to well, whatever that is. That is 9 divided by 12. That's 3/4. Okay, 3/4%. That's the monthly interest rate, which means each month is the interest rate would be let's see, 3/4. Our as a whole, then this isn't our. This is just the interest rate. Now the ratio then is going to be equal to 1 plus this is 0.075. So the entire interest rate is going to be I need to make it dry up. 1.0075 because 3/4 is 75%. So then so it's less than 1%, is 0.07 and then 5. So this is the value of R, because the rate is always 1 plus whatever the percentage thing is. So now we have all the required numbers, okay, and we're going to plug it into this formula where I will write it down because it's, so the total sum of the annuity, okay, Sn, where n is 120, is going to be equal to A1, which is 100, times 1 minus R, which is that thing, 1.0075 raised to the power 120. And then divided by 1 minus the same number. We're following this formula here, 1 minus 1.0075. In other words, it's a negative number. But anyway, so that is, so let's type this out on the calculator. Let's see, we have, the top is 1 minus, 100, okay? Maybe I should do it on this side. Can you see this better? Yeah, I guess, kind of. Okay, so I'll type in 100 times 1 minus 1.0075 raised to the power, oops, wrong button, raised to the power 120, 120, and then get out of the top and close parentheses. Okay, so I have typed in 100 times 1 minus whatever raised to 120 power, close parentheses, divided by the bottom, which is minus, 1 minus that is just minus 0.0075. Where's my minus? I don't have minus. Okay, I have to go back and get the minus. Negative sign, okay, here's the negative of 0.5. Okay, so divided by negative 0.0075, so close parentheses. So that should be okay. I have the negative sign. That is 19,351 is what I got. 19,351, yep, and that is correct. And with that, we have come to the end of this section. Now, please do all the examples yourself as well. Make sure you know how to do them. And once you know how to do them, then it shouldn't be have any trouble doing the homework. So for homework, please do problems 7, 11, 15, 21, 25, 33, 35, 39, 41, 45, 47, 51, 55, 59, and 61. Now, I'm not going to go over the homework because they all follow these formulas exactly. So as long as you identify what A1 is and N is R is, then you should be okay. So that should mark the end of this section.